A stem and leaf plot is a special table where each data value is split into a stem, the first digit or digits, and a leaf, usually the last digit. Let's look at this example, and we're going to construct a stem and leaf plot. We first want to organize the numbers from smallest to largest, and it is already done for us. Now the first part of the number is going to be our stem. Looking at the values in the data set, we realize we have a range of 1 to 4. So for the stem, I'm going to put my numbers as 1, 2, 3, 4, since the front number of each data value has either a 1, 2, 3, or 4. For the leaf, I'm going to look at the last digit. 15 is represented like this, 1 on the stem part and 5 on the leaf part. So this represents 15. 16 is going to be written like this, 1 and a 16. So this represents 16. We have 21, the stem is 2 and the leaf is 1. 22, the stem is 2 and the leaf is 2. For 23, we have the leaf is 3. 26 and 26 appears twice, so we have to represent 2 leaves with 6 and 6. We have 30, so that's going to be a stem of 3 and a leaf of 0. 32, a stem of 3, a leaf of 2. And finally, 41 is represented by a 4 for the stem and a 1 for the leaf. In this case, our leaf unit is equal to 1. That means this number on the leaf side represents the ones place. So the reader knows 1, 5 represents 15. Example, consider the grades for a class written in stem leaf form. What was the original data set, assuming the leaf unit is ones? Now, I want to translate this back to the original data, so we'll start with the stem. 1, 2 represents 12. 1, 3 represents 13. And we could continue the process and decipher the original data set. 2, 1 represents 21. We have 27. 3, 3 represents 33. 3, 4 is 34, 35, 37, 4, 0 represents 40, we have another 40, and finally we have a 41. So this is the original data set. Let's look at more definitions. The median, denoted with the letter M, is the middle value of an ordered set. The minimum is the lowest value in the data set, and the maximum is the highest value in the data set. In order to find the median, we must first order the data set from small to big. Then we have to find a number such that there are exactly as many values above it and below it in the data set. Example, sibling data 0, 2, 1, 5, 7. Here n is equal to 5, which means our sample size is 5. Find the median, minimum, and maximum. First, we need to order the data set from smallest to biggest. So we'll say 0, 1, 2, 5, 7 is the order from smallest to biggest. The minimum is really easy to find. It's the smallest value. That is 0. The maximum is the next easiest value to find. That's just 7. Now the median is the number that's right in the middle, and you can clearly see that 2 is in the middle where we have 2 data values below it and 2 data values above it. So the median is equal to 2. Example, find the median, minimum, and maximum. Again, we have the sample size is equal to 7, and I want to arrange these values from smallest to biggest. The smallest number is -3, then we have -1, 0, 5, 5, 7, and 9. To find the minimum, it's going to be the smallest value, that's just -3. To find the maximum, that's the largest value, that's just 9. The median is the number right in the middle, so we have 5 is directly in the middle with 3 data values below it and 3 data values above it. The median is 5. Consider the following. We have the data set 12, 3, 11, 17, 5, 4, 201, and 0, where our sample size is 8. Find the median. In this case, 8 is an even number, so we're going to have to figure out what to do with the median. We will arrange the data values from smallest to biggest, and we'll have 0, 3, 4, 5, 11, 12, 17, 201. And now, in order to find the median, we'll look for the number that's right in the middle. In this case, we have two numbers in the middle, 5 and 11. If we have an even set to find the median, we have to add these two numbers and then divide by 2. So if it's an even set, add the two numbers in the middle and then divide by 2. This gives us 16 divided by 2, which is 8. The median is 8. What is a percentile? Well, let's consider the 95th percentile. Let's suppose we took an exam and we scored at the 95th percentile. That doesn't mean we had a score of 95%. The 95th percentile means we beat 95% of the population. So of the exam, we beat 95% of the students who took that test. The quartiles divide the data set into quarters. The first quartile, Q1, has 25% of the data below it. The second quartile, Q2, which is also known as the median, has 50% of the data below it. And the third quartile, Q3, has 75% of the data below it. We therefore say that the third quartile is also the 75th percentile, and the first quartile is the 25th percentile. Example, for the following data, find the minimum, Q1, median, Q3, and the maximum. First thing we want to do is to find the easiest values to look for. The minimum is the smallest value, and that's going to be the 20. The maximum is going to be the highest value, and that is 40. But make sure the data set is arranged from smallest to biggest before you determine the minimum or maximum. Looking at the numbers, I notice that the sample size is equal to 14. So we'll look at the two middle numbers, and that's going to be 32 and 33. So to find the median, we're going to take those numbers, add them up, and divide by 2. So the median is 32.5. To find Q1, we have to cut the data in half and find the median of the first half. The median of the first half is 28. It is directly in the middle of the first half, so Q1 is 28. Q3 is going to represent the median of the second half, so when I split the data in half, the number that is directly in the middle is 38. So Q3 is 38. So we have the min is 20, Q1 is 28, the median, or also known as Q2, is 32.5, Q3 is 38, and the maximum is 40. Let's look at the box plot. A box plot is a way to display the data using the 5-number summary and noting any outliers. The 5-number summary is the following. The minimum, Q1 or the first quartile, the median, Q3 or the third quartile, and the maximum. So the 5-number summary is the minimum, Q1, the median, Q3, and the maximum. Here is a box plot. Notice that in the center we have a box. That's where the majority of the data lies. On the left side of the box we have a whisker, and that is where the data value extends all the way to the minimum. And on the right side we also have another whisker, and that's where the data value extends to the maximum. If you look at the regions of the box plot, the minimum is the lowest value. This edge of this box is Q1. The middle of the box here is the median. The right side of the box is Q3. And so the box plot allows us to visualize the amount of spread the data has. The majority of the data is in the box, while there are a few data values that are to the left and to the right of that. We also have the box represents the interquartile range, or IQR. The interquartile range, IQR, is equal to Q3 minus Q1. So to find it, we just need to subtract the third quartile by the first quartile, and that will give us a range for where most of the values are. Remember, quartiles separate the data into quarters. So from the minimum to Q1, that's 25% of the data. From the minimum to the median, that's 50% of the data. And from Q3 to the minimum, that's 75% of the data. You could also think of it in another way. From the minimum to Q1, that's 25% of the data. From Q1 to the median, that's another 25%. And from the median to Q3, that's going to be another 25%. From Q3 to the maximum, that's another 25%. And from that, we can conclude that the interquartile range consists of the big portion, or 50% of the data. Now the question is, why are box plots important? Well, they allow us to see the shape of the distribution. Here I have 3 examples of box plots. Notice that the tail is longer on the left, so this is known as left skewed. This means that most of the data is on the right side, but very few people are on the left side. In the center here we have a data that's pretty symmetric. We have the tail on the left and the tail on the right is pretty much the same distance, so this is a data that's symmetric. In the last example, the tail is longer on the right side, so this is considered right skewed. Now again, remember, if the tail is on the left, it is skewed left. If the tail is on the right, it is skewed right. Let's figure out how to draw a box plot. Step 1, make a uniform scale along the horizontal axis. Step 2, draw vertical lines at Q1, the median, and Q3, and we want to enclose these lines in a box. Step 3, we want to find the values of the lower and upper fences, and we'll calculate those in the next slide. Step 4, extend horizontal lines, or whiskers, from Q1 and Q3 out to the data values just inside the fences. The key word is just inside the fences. So you want to select values that are above the lower fence and just below the upper fence. Step 5, indicate any outliers with an asterisk. Step 6, title and label the box plot. Note, outliers are values that are extreme in relationship to the rest of the data values. In order to find outliers, we must first determine the first and third quartiles of the data, then compute the interquartile range IQR, which is calculated by taking Q3 and subtracting Q1 from it. Then we can determine the fences. The lower fence is equivalent to Q1 minus 1.5 times the interquartile range. The upper fence is equal to Q3 plus 1.5 times the interquartile range. If a data value is less than the lower fence or greater than the upper fence, it's considered an outlier. Example, every 6 months, the United States Federal Reserve Board conducts a survey of credit card plans in the United States. The following data are the interest rates charged by 10 credit card issuers randomly selected for the July 2005 survey. In this example, I want to determine the 5-number summary of the data, determine if there are any outliers, and we will draw a box plot. The first thing we need to do to find the 5-number summary is to arrange our data values from smallest to biggest, and we will do that first. I have arranged the data values from smallest to biggest. We have 6.5% all the way up to the highest 14.5%. Now remember, the 5-number summary is the minimum, Q1, the median, Q3, and the maximum. I always start by looking for the minimum first. That's going to be 6.5%. The maximum is the 14.5%. After I find the minimum and the maximum, I always look for the median next. Remember, the median is the number in the middle. And since we have 10 data values, that's going to be the 2 numbers in the middle, and we'll have to add them up and divide by 2. The 2 numbers in the middle are 13.3% and 13.9%. We're going to add these up and divide by 2 to find the median. The median is equal to 13.3 plus 13.9 divided by 2. And this gives us a median of 13.6. The median of the first half is 12%. Looking at the upper half, the median is 14.4%. So here is my 5-number summary. We have the minimum is 6.5%, Q1 is 12%, the median is 13.6, Q3 is 14.4%, and our maximum is 14.5%. Next, we're going to determine if there are any outliers. In order to do that, we'll have to look at the lower fence, and we'll have to look at the upper fence. The lower fence is equal to Q1 minus 1.5 times IQR. The upper fence is equal to Q3 plus 1.5 times IQR. Let's recall the 5-number summary. The minimum, Q1, the median, Q3, and the maximum. And our numbers are 6.5, 12.0, 13.6, 14.4, and 14.5. We'll find the IQR first, the interquartile range, and that's equal to Q3 minus Q1. So we're going to take 14.4 and subtract 12.0. This gives us an IQR of 2.4. Now, since we have found the IQR, we can use that to calculate the lower fence and upper fence. The lower fence is equal to Q1 minus 1.5 times IQR. Q1 is 12, so we'll put 12 minus 1.5 times the IQR, which we already know is equal to 2.4. We can enter this in a calculator, and this gives us 8.4 as the lower fence. The upper fence is equal to Q3 plus 1.5 times IQR. And Q3 is 14.4 plus 1.5 times IQR, which again is 2.4. Using our calculator, we get the upper fence is 18. The lower fence is 8.4, so we'll write it down. And the upper fence is 18, and we'll also write that down. To see if there's outliers, we have to check if anything is outside our property. Is there anything that's less than 8.4 in the data set? I look at my data set, and 6.5 is less than 8.4, so 6.5 is an outlier. 6.5 is an outlier. And then I look at the upper fence. The upper fence is 18. 18 is all the way over here, and everything is inside my property less than 18. There's no outliers above 18, but there is one outlier that's below our lower fence 8.4, so we only have one outlier, 6.5. To draw our box plot, we need the 5-number summary, and recall the 5-number summary. I'm going to draw a line along the horizontal axis, and we'll have our scale. I'm just going to go from 0 to 15 to include all of our data values. Now the first thing we need to draw is Q1, the median, and Q3. Q1 is 12, so I'm going to draw a vertical line at 12. The median is 13.6, so that's going to be between 13 and 14. We'll draw a vertical line between 13 and 14. Q3 is 14.4, so that's going to be between 14 and 15. Remember, this vertical line represents Q1, this vertical line represents the median, and this vertical line represents Q3. We need to enclose these lines in a box, and now we need to draw our whiskers. To do that, we'll have to look at the lower fence. The lower fence is 8.4, and the upper fence is equal to 18. Now I'll need to find our data value that's just above 8.4 inside our property, and that's going to be 9.9%. That's the data value that's just within our fence, 9.9%, and I will graph my whisker up to that point. We have 9.9% as the end point of our lower whisker because that's just inside our fence. Now for the upper fence, we know that the value that's just inside our property below the upper fence is 14.5%. So I'll extend the whisker to around 14.5%. The last thing we need for this graph is the outlier, and recall the outlier was 6.5. So we'll plot 6.5 as an asterisk or a dot, and that's our complete box plot. A quick question for you. What do you think the shape of the distribution looks like? Is it skew right? Is it skew left? Or is this pretty much symmetric? So take a moment to think about that. Is the distribution skew right, skew left, or roughly symmetric? The correct answer is the distribution is skew left. It is skew left because the tail is much longer on the left side, especially with this outlier at 6.5. You are given a box plot and we want to find the 5-number summary. So pause the video and try that on your own. Looking at this box plot, we notice that there are no outliers. There's no asterisk or dot on the left or right side, so there are no outliers. The minimum is the smallest value, and that's going to be 5. Q1 is the left side of the box, and that corresponds to 10. The middle of the box here is the median, and the median is 16. Q3 is the right side of the box, and that corresponds to 19. And the maximum is the highest value, and that is 20. In some situations, we might have a data set that has many values in it, and it will be unreasonable to do the calculations by hand. For this example, I'm going to find the 5-number summary using technology. In real life, statisticians use technology to calculate the 5-number summary. They rarely do the work by hand. So let's do the problem using technology. You will find a link in the homework assignment. To find the 5-number summary, enter the data values in the calculator and select Calculate. The computer gives us the minimum, Q1, the median, Q3, and the maximum. So use this calculator if you want to quickly calculate the 5-number summary. We'll start by the definition of mean or average. The mean is simply the sum of all the values in the data set divided by the number of values. In statistics, generally speaking, we calculate the mean for either the sample or the population. The sample mean is denoted with the symbol x bar. To calculate the sample mean, we have x bar is equal to the summation of x divided by the sample size n. This Greek symbol sigma here just means I need to add up all of the data values. So don't be scared of the notation. This sigma notation just means add up all the values. On the bottom we have n, which is the sample size. This is a lowercase n, and that represents the sample size. To calculate the population mean, we use the Greek symbol mu. And the formula is exactly the same. We have to take the summation of the x values and divided by the population size. Now we use a big N for the denominator because big N represents the population size. So the formula for both population mean and sample mean is essentially the same, except we use mu for the population and x bar for the sample. Example, consider the sibling data, find the mean of the sample. To find the mean of the sample, we will use x bar is equal to the summation of the x divided by our sample size. In this case, we have 1, 2, 3, 4, 5 individuals surveyed, so the sample size is 5. And so we can add up the values, 0 plus 2 plus 1 plus 5 plus 7, and divide it by our sample size 5. This simplifies to 15 over 5, and we have, this is equivalent to 3. So the average is 3. Example, find the mean of this sample data, the number of pounds lost or gained over the Thanksgiving holiday. Some people are on diets so they lose weight, while others enjoy their Thanksgiving break and might gain a few pounds. Now let's calculate our sample mean. Again, we'll use the symbol x bar since we're considering this as a sample. If this was a population, then we would use mu. X bar is equal to the summation of our data values divided by our sample size. And in this case, we have that the sample size is 7. So we'll take negative 3 plus 5 plus 0 plus 7 plus 5 plus 9 minus 1 and divide that by 7. The numerator simplifies to 22, and now we have 22 divided by 7, and that is equal to 22 over 7 is approximately 3.14. So we're going to round this to about 3.14. On average, these individuals gain 3.14 pounds over the Thanksgiving holiday. Let's look at our statistics calculator and try some values out. I'm going to enter 45, 47, 48, 49, 55. So I have 5 values, and if you look at the values, it is clear that the average is going to be somewhere between 45 and 55. So we'll calculate the average, and the average is 48.8, which is between 45 and 55. Now, let's say we have an extreme outlier. Let's suppose instead of 55, we'll replace it with 1 million, and we'll see what happens to the average. This is an extreme value compared to the rest, so I know the average is going to pull towards the larger n. So we'll calculate, and the average does get pulled towards the right because we have an extreme. Now let's try this again, and instead of changing the 55, let's change the 45 into a 0. What's going to happen to the average? Is it going to get smaller, stay the same, or get larger? We'll calculate the average, and the average gets smaller. The mean gets moved towards the direction of the outlier. Now look at the median. The median is 48. And if I were to change this number back to 45 and calculate the median, it's still 48. If I were to change the 55 into a really, really huge number, the median is still 48. It doesn't move at all because the median is just the middle number. So the median is not affected by those extremes. What are the disadvantages of the mean? The mean is affected by outliers. The advantages of the mean. It takes into account all values in the dataset, and it is commonly used and easy to calculate for small data sets. If our distribution is normal or bell-shaped, the mean, median, and mode tend to be in the center of the distribution. If there's an outlier that is extremely small in comparison to the rest of the data, the mean tends to pull towards that direction. If there's a number that is large compared to the rest of the data, the average tends to pull towards that direction. The mean is affected by outliers. It tends to move in the direction of outliers. The advantages of the median. It is more robust or resistant to outliers. The disadvantages of the median. It only takes into account one or two values and ignores all the other values.